Hey, good evening, everybody. Let's get started. 7:30. We have quite a lot participate. That's good. So we are starting this thing, your logic gates and transistors model, and how to make combinational circuit in today's topic. I hope you have reviewed the videos and lecture notes and have question for me. So let me know, or any other question in that matter. No, yes, maybe.
Can we go over some of the problems from maybe lectures 1 and 2?
Yeah, sure. We can do that. Definitely. So, and, anything specific problem you have in mind?
Yeah, just kind of there's one where we're asked to write the content um, of each address in memory for the text and then also for the data. And I'm just wondering kind of how we come up with some of the content for the data um, that's stored in the memory. For
Oh,
that's number 13, I think.
yeah. So for that problem, by the that type of problem won't be coming in the exam time. Uh, Mainly because those problems are to tune yourself onto our test case generation for the projects. Okay, so don't expect that type of problem in the exam. Secondly, this is more like an reviewing your concept on how you trace your assembly level programming. Like, remember CS47 or assembly programming, that you basically if you want to read another's code written in assembly, how do you go through that problem? Okay, so this is mainly that part. I can definitely uh, explain that. Let me bring that up. So this is 14. Where is that?
I think it's lecture 1, 2, number 13.
Yeah. I'm just trying to pick up the file. Number 13. Let's see.
Like we don't have to do all of them, but maybe if we could just get to
Right. The overall
some.
process, right? Let me just share this with you. So we are talking about this one, right? And then you see that it is more like given an assembly code, how you convert it into first of all into the somewhat high level statement, somewhat, so that know we know about the operation being done, right? So that's what we are doing here on the pseudocode column. Given each of this assembly code, we're trying to see what they're doing. Like, this is like R0 equal to R0 plus 1, and we know all the registers are resetted to 0 in the first place. So this becoming R equal to 1, R equal to 2, and R equal to 3. Then with the Louis operation, by the definition, look at that CS147 TVs, what the Louis operation means, and you will see it's basically in the upper 16 value, it is loading that. So this statement is practically doing this operation, loading this bit pattern onto the register 3. So in this way, you basically translate first into some high level pseudocode, so that it kind of clear up your mind that what is going on in that sense. And then you basically, from that, It is the same code. Okay, let's see. Okay. Now here you see in that whole problem, your store word is the only one which is storing into sorry, I take it back, not only stored word. Stored word is one of the instruction that writes into the memory, and there it uses the push as well. So what you need to do, uh, go to the push, that instruction description, and you will see it says that it starts from the top of the stack. So that means you need to go to the definition of the stack. Like I think previous to that page, we have that memory usage convention in CS147 DV, that instruction set architecture. It says that, hey, my stack pointer start at this address. So that means anything push is going from, I believe, the registered 0 content into that stack address. So these are the live instructions. So you break it down and then follow through the code. So there is a loop. That means in this statement, it is looping through with some certain condition. So R4 not equal to R2. So that means you need to actually keep track of the values of this R4 and R2 in each iteration and follow through the changes. So maybe you can actually maintain the spreadsheet with this register name and the value corresponding on each iteration it makes, so that you can build up ultimately the memory address where it is the value of R1 being stored, and that goes into the answer here. Okay, so this is the general direction you want to move.
Yeah, that makes sense. And I'm guessing because I think the problem statement said this was uh like I'm just a little confused. Like how much is being stored in the content of the memory? It looks like it's 2 bytes, right? Or or
This is the data address, right? And this is the content on that memory. So this is simple value like hex in the hex code, by the way. The hex it is being, you can use a decimal format as well. It is just saying that main part is that whether you are calculating the corresponding address location correctly or not, and what would be the value of that value that's stored there. It really depends on what is being at certain iteration, what is being like value of R1 that is going into that memory address driven by the R3, and what is the value of, for example, R0, which at that point, which is being stored at the stack pointer, the memory address pointed by the stack pointer.
okay. And I was just expecting 4 address for R3 to only take up 4 addresses, but it looks like it's taking up 5. Am I missing something?
Addresses, 4 addresses. So this loop is going from, I believe, let's see, R2 is what? R2 was
Oh,
0,
but it's looping. I'm sorry. Yeah, it's
right?
doing it over and over again.
Right,
Okay.
exactly. Till this condition is met. I believe it is like 5 times looping, and it is storing 10 different value at 10 different location in the memory through this instruction and this instruction.
Okay. Yeah, I definitely see it now. Thank you very much.
So this is a good exercise to refresh your assembly conception and how basically this instruction affects the memories in the overall system and how things works internally. So that in the project 2, when you'll be writing some sample assembly code and turn it to the machine code, and you want to know what is the outcome of that program would be, this concept will help you there.
makes sense. Thank you.
Okay. So, okay, now let's move on to how about like we just did some circuit design, right? These lectures supposed to we're supposed to review how the combinational circuit design would take place. Let's make an exercise of that. Let's take a sample problem. I'm just putting that problem onto the whiteboard, class whiteboard. You can go there as well to look at the problem statement. So we're trying to design this circuit Okay, so this circuit, which basically takes a 4-bit number, input signal are WXYZ, with W being the MSB side and Z being the LSB side. Now it detects the 4-bit number values which are less than 3 or greater than 12 or divisible by 3. So that means if those conditions are met, either these or these or these, output goes 1, otherwise output remains 0. Now you need to implement this circuit with a NAND only logic gate. So you cannot do anything else. So you can assume multi-input NAND gate as well. Like you don't need to use 2 input, you can use 3 input, 4 input NAND gate as well. So given this problem, what you need to do, come up with a logic circuit diagram. Okay, so what I'll do, maybe it can be a good group work. So let me open up the breakout room with your study group, and let's take about maybe 20 minutes to do so. This is a large problem, so you need to discuss, draw the truth, to like come up with the truth table, come up with solve the K-map, come up with the basic equation, then convert that into the NAND only equation, and then only you can draw a circuit diagram, NAND only logic diagram. So let's take 20 minutes for doing so, and then we'll check with one of your study group or couple of study group what their solution is. You can use your collaboration doc to communicate with each other, and let me open up the sharing screen facility so that you can actually share your screen with each other. So here it goes. Hey, how about study group 11? Do you want to share what's your experience and how far you went through? And
Uh, yeah, we got the answer. What we expect to be the answer.
okay,
Uh,
sure,
it's a pretty lengthy process. Let me screen share
sure.
my screen. Let me get the first one though. So we first drew out a Carnot map and populate it with the correct value. So we have three conditions in this question. We have values that are less than 3. So we want to put ones in the 0, 2, or 0, 1, and 2 cells. And
Mm-hmm.
then the other condition is greater than 12. So 13, 14, 15. And then divisible by 3. So 3, 6, 12, 9. And
Okay.
then that's all of our ones. Now we visually inspect our K map and find each group. We
Mhm.
put into sum of product, and then we uh, did a bit of algebra and simplified it just a bit. So we got this bottom equation,
Mhm.
and then we built that into standard gates and standard logic, combinational logic. So we have, well, if we look at the equation we have two sides to it. We have the one where W is true, and we have the one where W is false. So
Okay.
then we have essentially separate into top and bottom. Here's the line, I guess. So the top one is where W is true. The second one is W is false. And then we ORed them because they're ORed at the end. And then here's the output. And
Okay.
then after that, we create our NAND equivalent. So for example, here's a AND gate in the form of NAND logic. And
Mhm.
then let me screen share my other screen. I think this is the correct screen. So then we uh, convert it into NAND only logic. So basically, we're converting OR gates to this equivalent of
Okay.
just NAND gates. And then AND gates is, as before, just this combination. And
Mhm.
then an inverter is just a NAND gate with both inputs tied together.
Okay.
And
Okay.
then, so we have essentially the same thing, just a lot more messier because of time. We have our top and bottom line. So top is the W is true, bottom is W is false, and then the complete right side is the output, which I'll just put out right
Okay.
here.
Okay. So definitely we cannot test it right here at a limited time. It seems like you have followed the steps, except you didn't come up with a truth table, right? You just directly put things on the K map.
That's right. I just went directly to the K map because it is visually much faster.
Yeah, that's true. But yeah, formal step would be to create the truth table first and then create the SOP out of the truth table and then to go to the K map. That's the formal process. Yeah,
Right.
you should follow that one as well. Definitely in the crunch time with the faster solution would be, this is a simpler problem, so you can go directly to the K-map and put the numbers there and ballpark that. And yeah, and maybe another idea would be to, when you come up with the expression, then right there you can actually come up with, like, convert them in the NAND only expression itself using the De Morgan theorem, De Morgan transformation, and then it would be a easier problem for you to draw the circuit. So make the expression first with the NAND only. Other than that, seems like okay. Your problem is, that's good, wonderful. Thank you very much for sharing.
Right. And an issue that doing this way falls into is because uh, once we convert it into NAND only, we have a lot of redundant cases. So we have like two inverters in a line
Mhm.
because of converted NAND logic. So this isn't completely optimized, but it's close to being optimized. Like we haven't done that part yet, but essentially yes.
Maybe you want to just put your circuit onto the Verilog and simulate and see if it is working okay or not. We'll see. Okay. Thank you
Right.
very
Thank
for
you.
the solution.
Professor.
Yes, Matthew.
Can you discuss a little bit about, like, especially in this example, when we're going to be worried about don't care terms, or if any don't care terms are going to exist in the truth table or during the K-map process?
That's a very good question, Matthew. So, don't care term is coming from the fact if a problem statement from the problem statement you need to identify if certain combination cannot come into our as input space, right? For example, this problem, right, this problem has don't have such scope. It says it will detect 4-bit numbers, and out of those all the possible combination of 4-bit values, we want to detect the values of this. So it doesn't actually have that scope. Another example, the example we did in the lecture, is that you want to convert like that BCD, right? One digital value to the BCD code. So basically it says your problem space is from digit 0 to 9. Digit 0 to 9 convert into the, sorry, it's not BCD, it is the XS3 example. So each digit is represented as a +3 value. That means 0 represent as 3, 1 represent at 4, 9 represent at 12, that bit combination. From that problem statement, it is obvious that this problem doesn't want you to deal with more than 9, only 0 to 9, because it's a digital, it's a digit, it is handling individual digits. So in that respect, it becomes the from value 10 to 15 in the truth table of that 4-bit combination becomes a don't care. First of all, like we have had 10 digit, that means we have to have 4 bits to represent them. We cannot live with the 3 bits. So 4-bit log base 2 of 10, you take a ceiling, it becomes 4. But with the 4-bit, you can represent actually 16 different things, but you are trying to represent 10 different things. So that means 6 rest of the representation becomes a don't care. So that's the general guideline. Like you look at the input space and see how many bits you need to represent that many input combinations. Okay, and you see if it is covered all the space, like you need 4-bit and you need to represent 16 different things, then there is no don't care. But you are using, like, let's say 5 bits and you need to represent like 24 different things, then you have 8 don't care terms out of that whole input spectrum. Make sense, Matthew?
Yeah, I'm kind of hearing like there, if you can clearly identify a constraint on the input
Um,
space, is that like what you're saying? Like,
this is that just a general, but so this is more like an art than science, if you want to say in that way. Like it is really from the problem statement and analysis of the statement, you need to identify how many bits you need as an input. Okay,
okay,
and then consider what are the number of things you are going to represent at the input side, and compare it, like what is the maximum number of things you can represent with that number of bit, and what are the number of things you need to represent as an input to that specific circuit. If there are excess number of representation, they become don't care.
okay, yeah, it's clear. Thank you.
Okay, so let me share my solution to that little bit, and it can be different solution, as like it can come up with a different equation and stuff like that. So you don't be worried if your solution is not similar to this what I want to do there. Let me see if I can copy this. Oh. Okay. All right. Mhm. Just give me a minute. So this picture download. Okay, one can be like this. Oh, this is really messy. Ah, okay. And another can be like this. So if basically depending on which part you are grouping, there are possible two different groupings of essential prime implicant, and depending on which one you pick up, you can come up with a different solution. So here, what I have done, I came up with the basic equation there, okay, and then each of the term I um, use the De Morgan to convert into NAND. The whole thing is something or something or something or something. That means with the De Morgan, it becomes like those term inverted and condition, and whole thing is a inverter. So entire outer logic is a NAND logic, big NAND logic, and then individually we went through. I went through the corresponding conversion, converting them into the NAND as a so that becomes the solution, and the picture. If I draw the diagram, then it would look like. I hopefully this is not coming up messy. Yeah. So this one would become something like a NAND, which uses like some of the 3-input NAND gate and some of the 2-input NAND gate and so on and so forth. And that becomes a NAND only logic circuit for this one. So at this point, let us take a quick break, 5 minutes, 8:20, 21-ish, we'll be back. And I'll show you how to load it into the Verilog and do simulate and verify the functionality of this. Okay, let's get resumed. And as I said, like we can actually represent the circuit in the Verilog and try to verify the functionality quickly. So to do that, let me show you how we can actually, from a logic gate circuit, we can make a Verilog description. Which one am I sharing? Share screen. Share. Okay. So really, like if some of these internal these logics, let's just name them as a where, right? This W2 is basically, we are taking W and X whole bar. So we are taking W and X and making whole bar here. So NAND through the NAND. So what we can do for this guy, we can write something like an instance name N8, for example, followed by a NAND. NAND is a Verilog keyword, and we say that output W2 is a function of W X. Okay, so this one would basically represent a NAND gate which evaluating NAND between W and X logic and assigning to W2. Now, what is a W2? Really, W2 in the Verilog is an where. So we can define a where W2 in the Verilog and use that as an evaluating the logic values as if this is a real logic gate at the electronic world, real logic NAND gate, and we are simulating that. And similarly for the, let's take this one, W4, right? W4 is a logic between three logic gates. So we can make a NAND and W4, and which is become like, let's say XYZ, right? X, Y, Z bar. So Z bar, again being aware, like I just name it here, like this, let's say output of this NAND gate is represented or connected to the wire named Z bar. So essentially my wire list would have another wire called like Z bar and so on and so forth. So in this, with this idea, what we can do, we can actually create a project in the Verilog, and then we can simulate it. So I'm sharing this screen, hopefully. So you guys are seeing my model sim, right?
Yes.
Okay, okay, great. So, so the circuit we just described here, we can write with bunch of NAND, bunch of NANDs, and wires between them, like here all are the different wires, intermediate wires, and we have the primary input WXYZ and a primary output out, so that's what becomes like a out, and WXYZ with the input WXYZ and output out, and bunch of wires, and they're just being connected like an AND. Oh, my bad, I actually reversed this sequence. This one should be formatted like this: NAND followed by N8. This is instance name. Okay, get name, instance name, NAND N10. Okay, so then it's defining the circuit, the logic circuit, logic connection. Now we need to test it. So I defined a test bench, something like this. Since our domain is a 4-bit number, that means we are talking about 0 to 15. So in a for loop, what I'm doing is counting using a counter variable I, which is an integer type. I am simply counting from 1 to 16, okay, and putting it in the as an input in the input register. So what is this input register? This one is a 4-bit register storage, which then will, I is being the 32-bit, it will pick up the LSB side 4-bit and assign to the input register. And then I start with 0 and then loop through 1 to 15 in a for loop. So, and after each 5 nanosecond, I am updating the value, and at the end of the loop, after 5 nanosecond, I'm stopping it. Also, I have, so I am driving this, this whole instantiation of this circuit from a test bench with using the register in range, which are connected with a bitwise, that W for this module, WXYZ, this module, this independent input terminal are connected to the bit in range 3, bit in range 2, in range 1, and in range 0. So we are just picking up 4-bit, driving into this WXYZ of this circuit, WXYZ of this circuit. And for an observation of the output in the test bench, I have one wire out, and that is being connected to the out wire. So that's the explanation of the test bench here. Now let's compile everything and then go to the library and let's load the test bench. And let's make sure that we have, okay, I have this waveform outside. That's okay. 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 So I'll add these two in our waveform. And let me explain an interesting feature of the model sim well at this point. It's called data flow window. Okay, let's bring out data flow window. And in the data flow window, what we can do, we can actually, let's add it, like click it, move it here. Okay, so it actually shows you, or at least try to shows you the logic circuit instantiation diagram. And if it is a small circuit, then it will show you at a whole. If it is a big large circuit, then it will become like more like a hierarchical partition by partition you need to go in. That's a different story, but it's a very nice tool to debug the logic flow throughout your logic circuit that you have developed. And now let's go and simulate this. Okay, all right, simulate here. Okay. And hopefully it stopped, is it? What happened? Oh, okay, run all. Okay. And okay, here are the different numbers. Let me change the radix to maybe unsigned. So look at this logic functionality now. It's if it is 0, then my output is 1. If it is 1, output is 1. So far, so good according to our spec. So anything less than equals 3 would be 1, right? 2 is 1, 3 is 1. And anything greater than 12 equal to 12, greater than 12 would be 1. So 13 would be 1, 14, 1, 15, 1. Anything divided by 3 would be 1. So 12 is divided by 3, 9 is divided by 3, 6 is divided by 3. So they are at 1. And we have zeros for the other logic combination. So seems like this circuit is working okay. Now let's look at this data flow things. Like if you click on certain thing, right? If you, let me expand this window a little bit more. okay, if you expand onto this bus, 4-bit bus, then you'll see the individual bit values of 2, 3, and 1 of these in registers, and which are connected to the like WXYZ of the circuit. And if you go to the timeline, let's say we are testing on representation of 1, okay, you can see that, okay, these values, what are the logic value connects to which NAND instantiation in your circuit, and what are the data flowing through and crunching through the whole logic circuit to come up with the final result at these at the output of the whole logic. So it's basically, you can just follow through the logic on any of these this time point. Let's say if we just trying to see what is going on at when the value is 6. So you see the logic flow changes through the logic gate, and also, like, let's say on the 7, how the logic flows and evaluate through. So this is a good tool to actually debug circuits, logic circuit that you will develop, and visually at least you can see what are the logic crunching, data crunching is going on through your logic machine. So this is interesting. Please try it out with your solution and see if you can verify your circuit with the simulation environment. Question?
Professor, I have a question about,
Yes.
Do you expect us to always have the most optimized answer?
It depends on the question I give you. Like if you're talking about in the exam, right? In the exam, if it is given that, okay, give me the minimum number of gates, then yes, I'm expecting optimized number, right? Now, if I don't say anything, then okay, the constant is not there. However, keep in mind, like when you go to the real world, it is by default you optimize basically. Like otherwise, it's a high price circuit, more component, more pricey. So that keep that in mind. Maybe you can make that your goal. Like whenever you are coming up with a solution, make it as much optimized as possible.
Okay, thank you.
Okay. But exam point of view, that's what my point is. If I don't specifically ask you that, okay, give me the minimum number of things, optimized thing, then you can come up with a valid solution which gives you the output. That's fine. All right. So what's coming up then? What's coming up in the next lecture? Please review them. Let me see. Where is my? Here it is. Module. So we are in. Okay. So we are done with module 1. We are in module 3. So we are done with lecture 6. Supposedly, please make sure you went through once again if you are not unsure of the concept of the circuit design or how the gate operates, how the transistor operates, logically at least. Then next day, please review before coming to the class on the sequential logic circuit and storage element. Very crucial and important concept in the digital circuit world. It has 4 videos, but it's a little bit longer videos. So make sure you schedule your time accordingly. Maybe you will just watch one at a time and then take a break and so on and so forth. It's up to you how do you want to do it. But it more talks about that how we can combine this combinational logic element into something that can store and retain values. The one you talked always about, like the memories, like the RAM and this and that. What are the fundamental things goes on there, right? And what are the possible fundamentals? There can be many different things, but we'll be sticking to some smaller corner of that whole idea and try to grab around the fact that we can actually combine combinational logic to make storage element. That's what the discussion for this chapter, this lecture 7 is. Two sections: sequential logic circuit and storage element. So sequential logic circuit, and it has a reference to your textbook if you want to know more. Sequential logic circuit, that section talks about the idea of the sequential circuit, like what it means by a sequential circuit and how it differs from the combinational circuit. And then this is more like a theoristic approach of the sequential circuit. And then we will see that one element, one important and crucial element in any sequential logic circuit is the storage element. Okay. Now we move on to that part, like how we can build a storage element with the logic gates. So far we have learned, like we have learned NAND, NOT, NOR, inverter, etc. So how we can use them to build up a storage element, and from there we basically try to build up our concept from the very basic gate, like a buffer, like which is a back-to-back inverter, and can we use that as a storage, and so on and so forth. Then we go up to our study and see there would be certain configuration like a back-to-back connected NOR or NAND gate that can actually use to store logic value somewhat permanently till we supply the current there. Also note that there, like you see a lot of color coding here, which won't be very apparent if you're reading through the notes. So I strongly suggest you actually look at the video where I try to put some animation around these logic values, and so that your concept become clear about how this storage element is working, how actually it is storing an element there. And then we move from there, that basic concept, to build up some sort of truth table of the like storage element. We call it as a latch, and then from there we go with the NAND based configuration, which we call it an S bar R bar latch. From there we go another configuration to solve certain problem. Please make sure you are aware of the problem, what we are trying to solve with this NAND as a latch with the control. From there, we basically dive into some latch configuration, storage element configuration called D-latch with NAND. And finally, using a D-latch and SL latch, we go with the most important, one of the most important component in the computer architecture is called a flip-flop, a D flip-flop. Okay, so please make sure you get that concept right, how it is constructed, how it is being operated. With respect to I have discussed some of the like timing diagram along with that to explain the operation. Please make sure you actually go through that one. And also I have talked about different types of flip-flop, like a negative edge triggered flip-flop, positive edge triggered flip-flop. You need to make sure you get the conception right of what are they, how they differ from functionality point of view, from positive edge trigger and between the negative edge trigger flip-flop. And then we introduced another control circuitry on top of that, which is asynchronous preset reset, to make sure that we can start up any of the storage element in a known logic state, because that is very important in our sequential circuit design, which will be coming in the next lecture, lecture 8. How can we make a sequential circuit? How can we solve certain type of problems with the sequential circuit, and we cannot solve that with a combinational circuit? So that we'll see that in the lecture 8. So make sure you get this concept very crystal clear, and this will be used throughout this computer architecture course, and especially in your projects. Okay, question? Okay, if there is no question, then we stop tonight here and see you on next week. And make sure you have the quiz due this weekend.